Hello everyone, this is our video example related to our lecture where we talked about we derived the open system energy balance. So this is question 7.24 from the textbook, page 388. Turn to your textbook, read up the question, and then follow along with this example in this video. So here we have steam at 260 degrees C and 7 bar absolute is going to go through a nozzle. So it's expanded through a nozzle to 200 degrees C and 4 bar. We are told that negligible heat is transferred from the nozzle to the surroundings, and we're going to assume that the approach velocity, so the inlet velocity of the steam, is negligible. We are told the specific enthalpy of the steam at the inlet and the outlet. One is 2974 kilojoules per kilogram, the other is 2860 kilojoules per kilogram, and we want to use the open system energy balance to calculate the exit steam velocity. So let's draw a visual to try to help us understand what this question is about. We have this nozzle, we have steam coming in and then steam coming out as it's expanded. We have the inlet temperatures and pressures and the outlet temperatures and pressures. We are told to assume that the inlet velocity is 0, and we want to find the outlet velocity. So we're going to start with the open system energy balance, and we're going to use the compact form of that. So here it is. We have delta H plus delta EK plus delta EP is equals to the heat and then the shaft work. So in this case, let's think about what terms are 0. We're going to assume that the inlet and outlet are coming in at the same elevation, so delta EP is 0. We also know that there is negligible heat transfer that's given in the question, so Q is 0. We have no moving parts within this system, so our shaft work is 0 as well. So those three terms are 0. We have simplified our energy balance to delta H plus delta EK equals to 0. And now we need to expand out each of these terms, the delta H and the delta EK terms. Remember, for an open system energy balance, the delta represents the outlet minus the inlet. So in this case, we have one out and one in. That's pretty simple. So for the delta H term, we have M out minus H hat out minus M in times H hat in. So that's the enthalpy term, and then we do the same for the kinetic energy term with the single output and the single input. Now we have this mass in and mass out, but since we just have one stream in and one stream out by a simple mass balance, we know that the masses are going to be equal. But first of all, we also did assume that the inlet velocity is 0, so we have that term, the second term in our kinetic energy, going to 0. Using a simple mass balance like I mentioned, we know that the mass in is just equals to mass out, and I can just write it as a generic m dot. So by simplifying that, now I have m dot and then multiplied by the change in the specific enthalpies, and then you have the second kinetic energy term. At this point, you realize that I can just cancel away the m dot. I don't really need to know the mass flow rate. We won't be able to find it anyway. From here, I can rearrange for u out, which is what I'm trying to find. We are given h out and h in the question. So let's put it all in. This is rearranging the equation and putting in the numbers. And what you see down here is the enthalpies are given in kilojoules per kilogram. I'm multiplying it by 10 to the power of 3 here to convert it to joules per kilogram because I want to keep everything in SI units. So the SI units for energy is joules. By doing so, by keeping everything in SI units, I know I'm going to get some unit of velocity. And because I have everything in SI units, I know it's going to come out in the SI units for velocity, which is meters per second. So I don't have to worry about trying to figure out the units. Once I have the numbers, I know it will come out as 477.5 meters per second. So this is a relatively straightforward example, just a very simple example demonstrating the use of our open system energy balance. Again, the same approach, start with the energy balance, figure out which terms are 0, and then expand out the terms depending on how many inputs and outputs you have. Now, before we end this example, I want to talk more about this idea of a reference state. I've mentioned right off the bat when we talk about energy balances that it is not possible to know the absolute energy of anything. Energy is always in relation to something, in relation to some reference state. So similarly, in this case, when we talk about specific enthalpies, the specific internal energies, it is only relative to some reference state. And the reference state is picked such that your specific enthalpy or your specific internal energy is 0. For example, we have this table for carbon monoxide at 1 atmosphere, and we are given the temperatures, we are given the enthalpies at 3 different temperatures, at 0 degrees C, 100 degrees C, and 500 degrees C. How do we know where is the reference state, or what is the reference state that's picked for this carbon monoxide? It is where our enthalpy is 0. So that is at temperature of 0 degrees C. This means that this table of values was generated for carbon monoxide with a reference state at temperature of 0 degrees C, pressure of 1 atmosphere. So when you look at the specific enthalpy, let's look at the second value. So at 100 degrees C, when it says that the enthalpy is 2919 joules per mole, what it really means is that it is 2919 joules per mole relative to the temperature at 0 degrees C, or the enthalpy at 100 degrees C minus the enthalpy at 0 degrees C is 2919. So it's relative to that state. Sometimes you will see it written as a delta because really it is a delta with respect to the reference state. So the change in the enthalpy from the reference state of 0 degrees C to 100 degrees C is 2919 joules per mole. So generally, what we want is the change in the enthalpy or change in internal energy from one state to another for a particular species. We need to make sure that the enthalpy and internal energy values that we pick from whatever source that we get from are defined with the same reference state, and then we can use them concurrently. So that's the most important thing you have to remember when we talk about energy balances here. So let's go back to our question 722. We are given the enthalpies at the inlets and the outlets. So here are the values that were given: 200 degrees C 4 bar, 260 degrees 7 bar. So we have the two enthalpies over here. What this really means is that it is defined relative to some reference state. We are not given what the reference state is, but it doesn't matter. But there's some reference temperature and some reference pressure where our enthalpy is defined as 0 kilojoules per kilogram. And those values of 2860 and 2974 are defined relative to that reference state. So that's what the inlet enthalpy and the outlet enthalpies are. Eventually, it doesn't matter where the reference states are. It could have been up here. It could even have been in between. The reference state could have been picked somewhere in between or above that. It doesn't matter because ultimately what we care about is the change in the enthalpy, which is the delta H down there, as shown in the diagram. And that's not going to change regardless of the reference state. So as long as we have the same reference state for our inlet and outlet, we are going to be fine. We'll end up with the same solution. So that's all I have for this example. In the next example, we're going to start to go into how we're going to figure out these delta H's. For example, for this example, it is given in the question, but there are various tools and tables that we can use to actually look up our enthalpy values. That is where we're going to go for the rest of this course. So work hard, be smart. I'll see you next time.